Welcome to today's webinar about the structural design of photovoltaic systems in RFEM 6. My name is Andreas Hörold. I'm responsible for marketing and public relations in the company Dlubal Software. For instance, the German and English webinars, technical content of the website, customer projects, and so on. I will be the moderator today and I will answer your questions during the webinar. My colleague, Andreas Niemeyer, will be the presenter today. He's the head of product engineering by Dlubal Software. Okay, I say some words how you can ask questions. At first, I switch off my webcam that you can see the full screen. Just press the button with the question mark, then enter your question in that field, press send, and I will receive your question and I will answer you. The other way is to watch the entire webinar and then email your questions to info@dlubal.com. Okay, that's for the moment all from my side. I hand over to Andreas. Andreas, it's your turn.
Thank you. Then I take over with the topic structural design of photovoltaic systems, identifying challenges and implementing solutions with RFEM 6. This is a pretty interesting topic because it takes care about the challenges and requirements to engineers which working in this field. To organize this upcoming session, I created 5 points. In the first point 1, we discuss why photovoltaic systems challenge structural engineers today, and then we do the next points 2, 3 and 4 with looking especially on typical challenges in structural design of photovoltaic systems. We show how RFEM 6 simplifies everyday life here, from going from theory to practice, and at last but not least I show all mentioned functions also live in our programs. In the end, I give up a summary because in the discussing all points regarding these photovoltaic systems, I mentioned a lot of programs could be used, and to hold an overview here, I give a summary in the end. So, why photovoltaic systems challenge structural engineers today? As you can see here, I show you my mind map by creating this session. I thought, or I ask other engineers, hey, what is coming up in support? What is coming up from development? What is coming up from standards? And the most mentioned points are consideration of impacts, consideration of subsoil bearing capacities, determination of an optimal load transfer system, cold form cross sections, aluminum cross sections, investigation of module load bearing capacity, processing of similar models, create the documentation. So this is a lot of keywords what happening or what are mentioned in this case, and what the engineers have to suffer if they want to do photovoltaic systems. Of course, something is easy. On the other side, something is really difficult to find out. And if you are starting in this branch and you have to fulfill all these requirements, what happens? You have to think about and also to think about how you can do it quite efficiently. And so I will catch up this point now, what you have to fulfill and how we can help you. And in the first part is the point consideration of impacts. And if you start creating such models, you will get the question or come up to the question, which snow load I have, which wind load I have, which earthquake load I have, which load ever you have. And to give this a picture, I created here two pictures what explains you definitely which questions could come up. So in the left picture you see a photovoltaic system on a regular house with snow load, with an asymmetric snow load, and where you see the snow load is sliding down to the lower roof, which brings you to the questions, okay, which type of load you should consider there? Do you have to check also the building below? And this is not only a constant snow load, then much more what you have to check, and this is what should be solved in this type of tasks. On the right picture you see some destroyed photovoltaic system, I assume from any type of wind loading, and this brings you also to the question, which type of wind I should consider, which direction you should consider. Do you have some details? Wind can go below or not. There are special pressure situations, similar like on the left, maybe asymmetric one. What should be considered? And to go into this field to find the answer to this question, we created for our users, let's say, some smart tool on our website www.dlubal.com, where you find something close to Google Maps, and here we overlaid the Google Maps with all, let's say, civil engineering building impact loads like snow, wind, seismic, flood, tsunami. And if you pick on it, or if you search a place on world, you get for all covered regions what we are cover information on the left side about this load, and this information is of course the basic load, not the local load, but it helps you to go and start analyzing this stuff. For this we support not only Great Britain, then also all relevant countries of the world. Of course not every country gives a standard, but for this country we got a standard, we digitized it and pushed it into this system. And to show you how this could work, I open now a model. Open. You see here, maybe in the preview you already saw it. So now we are ready. You see we have here, let's say, the hull of a house with a photovoltaic system on it. And now let's come to the question, which snow or wind load of a specific place we have. And for this we implemented this interactive website also in our programs, and because we're speaking about the information of the model, it's not inside the model data and on the top. So we go to base data and go to model parameters, and you see you can define here any place. And for example, I place now the model maybe near our Dlubal headquarter in Tiefenbach. You see here we are in Bavaria, we have snow load zone 3 with this snow load, and if I confirm this setting, the process will suction out the address and also wind and snow load. Create here a map, and now we have the data inside the model. And for example, if we want to create now a wind load, we can go to the load wizards and go to the wind load, new wind load. Let's define it's a dual pitched roof, and we define the geometry by picking these corner nodes. And now you see the tool is recognizing the roof, the pitch, the parameters already given, and now it's asking or wondering in which load cases it should write it. I can generate it, and now after confirmation, oh, he wants to have a structure high maybe 7 meters. And now we can confirm it, and after confirmation we get here wind load cases, maybe, as you know, the different wind load cases for the structure to load it. And this is a lot of work you have to do, and here our program supports you with the local load on the structure if it fits. Now, and this is also possible for snow loads. Now let's come to the next topic, what means and what is a typical challenge in structural design of photovoltaic systems, the consideration of the subsoil load bearing capacity. What means, can I simulate the underlying system of the photovoltaic system? What is with foundations, etc. Of course, these are only words now, but to give you a picture, I created these two pictures, or prepared. You see on the left side our old farming house, and the people have installed here photovoltaic system on the roof. Of course, everything fine, no shadow, but on the left side you see the system is banded a little bit, of course, maybe because the roof is not plain, then curved according gripping or whatever, we don't know at the moment. But as engineers we should ask, should I consider this gripping? Is it important or not? I don't know. But I would have these thoughts, and brings me to the situation that I say, okay, maybe I should check the statics also below, not only the statics of the photovoltaic systems, or let's say we should also ask the client about. And on the right side you see something completely different, but it's a photovoltaic system or tables on the field. But why I selected this? I selected this because it's founded on some concrete stubs, and this brings me to the situation that also the engineers in this field have to answer the question about foundations. How many foundations I need? Is the foundation big enough? Is it too big? I'm efficient, because every foundation costs something, so the question should be clarified. And in this case, our program have also an answer. No? For the left side, to simulate the underlying construction system, up or down to the foundations if it's needed, I can answer it with RFEM. Our RFEM program is a free modeling environment. You have a free space. You can model everything from members, shells, solids together in one environment and find an equilibrium with all effects what are needed. And in this case, to simplify it, to explain it, I show you you have the photovoltaic system not supported on single supports on the roof tiles, then combined with the rafters of the roof to consider both stiffnesses and in the deflection. And on the right side you see also a picture of our program, the final output. If you are forced to say, is the foundation big enough or designed in a good way, we offer a foundation design for different types, which gives you also, or detects also the environment, or let's say it checks it, and this you can use for your design or for your final design to say it's good or not good. And how to solve this live in program, I show you now. For this, we go back to our model. I close this and open a modified one. It's 2.1, yes. And here you see now almost similar model with the hull of the house already with snow loads and wind loads. And also you see just here any deflection, so let's make it a little bit better visualized, so both in one, but let's use something maybe for snow load and say please show me only maybe the aluminum stuff. So this is our photovoltaic system. This is supported on the timber beams, and here it's modeled like this, that you have here primary the photovoltaic system, what is coupled to the beam, timber beam, and this timber beam supports the load to the lower beam and upper beam here, and this and produce the support forces on the top and bottom, what could be visualized here. For example, if we show the design situation and activate it and show support forces, then you see now you get the support forces from the photovoltaic system, what is maybe here on the outer side on top and then bottom for further design. Of course you can model the complete house below, it's only an example, but it should show you that you can model mixtures, not only the primary system. And the second part, if you also should check the soil below, for example, I prepared this system. It's a completely as a photovoltaic system. It's I call it always, it's a tracker system what shows always against sun to be quite efficient, but it have also the logic that it's maybe mostly have here a plane for the modules, and this plane is connected to a pile, and the pile is connected to the soil. And of course if you check the forces, you will see that you get here on the bottom maybe and make it a little bit more clear. Let's hide this. You see, if you check here static analysis, result by node for ULS, you get here a set of support forces with this extreme. So not only sub forces, then also bending moments, really big bending moments. No? And this bending moment should be taken from the soil or from any foundation, and for this you can activate in the base data here concrete foundations, and after you activated the concrete foundations you can define in the support conditions. So here where you check which degrees of freedom are fixed, you have a foundation option, and in this foundation option you can specify the foundation, if you have only a plate, a block or bucket, which material, which dimensions, which cover, which plate reinforcement, which block reinforcement, which soil properties. So we defined here gravel below and on lateral. And after designing this stuff, you get here an overview in the tables. You see, okay, for the ratio on this node you have the ground failure, sliding, equilibrium of structure, and so on, bending of plate, where you get the utilization and see, okay, everything is smaller or equal 1 and it's designed. So this tool gives you the option to design the foundations. And this brings me to next point, what means a typical challenge in structural design of photovoltaic systems is also the determination of an optimal support system or construction system. What I want to say with this, let's say this is do you have too much members in it? Do you waste material? Is the system rocking or oscillating, doing wind action or human action? How is the, let's say, module connected to the beams and so on? So it could be extended, this list, but to give it a picture. What I see, or in this field, really interesting is, and also challenging. So I really want to mention the challenging points. Let's say you see also here on the left picture a next variant of a photovoltaic system. It looks like a parking roof or a roof for cars, and you see it's done from this cantilever L-shaped truss beams. And I assume you have really to do engineering to find the right size of cross sections and not to bring in too much material. On the other side, I could expect that it's oscillating during erection on the bottom or doing wind. So you have to check different situations here. And if you don't, maybe it working in the first instance, but you will suffer something later. But only to open eyes what could appear here. And on the right side, let's say it looks pretty easy. It seems like a photovoltaic system on a roof. It's not fixed directly, then it's, let's say, only placed with a weight on the bottom, and the weight is finding an equilibrium to all impacts what are happening. Let's say to outstanding persons it looks clear, you need a weight on the bottom, but the question to the engineer is how heavy this weight should be, because if it's too heavy, you're wasting material. If it's too small, the wind will lift it. So all these questions appear to an engineer, and you should try to find an answer. And here again, our program can give you an answer. You have a free space of modeling. You can model weights, masses, members, shells, solids from different materials with different loads, with different analysis types, and to find results to decide if it's good or not good. So only here as overview, I put in the picture a bigger photovoltaic table and show internal forces according to the loads and support forces and deflections in the lower pictures to make some decisions. And this is exactly the point and the main work of us engineers here in this field. To make it a little bit more clear, I prepared following model, and here open determination of optimal system. If we open this, it's you see already the system with the utilization. We are 68% roundabout. The program already says, okay, design checks are green, so everything fine. But how you come to this picture and what you have to insert, and for this maybe start from scratch what the engineer did here. The engineer, let's say, defined primary load cases. So this upper part coming from the engineer. So he defined, let's say, a self-weight load case. The self-weight is coming from the section. So if you define a section, the program knows the size from the section and the material and can detect automatically self-weight. If you change it, it will be changed. He defines a module load, so from the glass plates, and maybe you see here you have only an input of 0.12 kilonewton per square meter defined over geometry, only over viewport and nodes. What means this? In background, the engineer only define here in our program the surface load, but in background the program applies this load only in the horizontal rails. this is done automatically and saves your time. This is a function what is quite efficient and is really a time saver, because this is easy to only pick node, define 0.12 and everything is good, but the program is doing the rest and it's done adaptively. Then also you defined wind pressures. So you get a tool to define endless of load cases you want to consider. Here upper wind pressure, lower wind pressure, upper wind suction, lower wind suction, snow load. And finally, these load cases are eaten up from our RFEM program in a design situation, what combining the results according to the laws what the combination standard is giving. Of course, not only once and more are existing. And this is generated into many load combinations. So this means 40 pieces for this variable load cases. And this, let's say, design situation is giving to design, and then you receive, by checking all these situations, these 40 load combinations on every X place of members, you get this result. So and by doing this, you can consider a lot of effects. You can consider different cross sections. So you see here, edit, the engineer of this model used different sections. So how I should do it, maybe, oh no, not see, like this. So maybe this section, you see it's highlighted in back, so maybe this is only the bracing, this is maybe here only this beam, here the piles, and every pile have also a different, maybe if we look here, material setting. So we have here maybe material for the bracings, material for the upper system, material for the lower system. We have here also the consideration of eccentricity. So for an outstanding person, it looks absolutely clear, like a drawing, that this beam is up on the top of the lower beams. But in structural analysis, this eccentricity have some effect. If you do it eccentric, you get additional forces, and it's not only eccentricity in one direction and in both directions. For example, also here the situation of pile to the rafter. You see you have here really different eccentricity dimensions. Further, you have also some connections between members to the other members. So the engineer here used hinge definitions to take care which type of forces are transferred here. So all these options could be considered in the environment of RFEM to find a good equilibrium and to find a design close to reality for your decision. And this brings me to the next point. What means cold form cross sections are easy to manufacture and inexpensive. So this is not a brace to cold form sections, and this is more a definition of requirement to us as engineers. So it said photovoltaic systems are made from cold form cross sections. What means for me, sections made from really thin metal sheet. And also what I see in the same logic, also cross sections extruded from aluminum. And which questions we have to this topic. So if I hear cold formed sections, for me is directly clear what I ask. Okay, these sections can buckle locally and globally, how I can consider it. and how I get the cross-section values and how can I bring it into the program. Many questions what can eat up weeks if you don't have the right tools for it. And I want to show you now how you can handle it in our program. So here in the picture you see an imagination about code-formed sections, and that how the buckle of such a cross-section could be. So if it's really thin, the compressed parts will go out of plane and cannot hold the state, and if the section changes its shape, it cannot, let's say, carry the load. And for this, let's say, we created a really adaptive design method what knows according to cross-section type which type of cross-section is here, and then it decides, okay, it can buckle or not according to the rules. And how this is working, so let's take a look on it. So I make a small example. For this I open a new model. Maybe I call it EE and define here the task steel design. Yeah, at first, with knowing nothing. So what I do is now let's open and make a 3 meter beam from a section, maybe create or change this section. Use here such a C section from material, from steel, 355. Maybe let's use zero cold solution. So cold formed is already defined, and give a size. So in this case, which size we take, maybe 120 to 50 to 1.5, so really thin. Radius I would say 3 millimeters, and the ellipse I would say 20, for example. No? So now we have the cross section inside, and I can define here a beam, maybe 3 meters as said. Let's define supports. So say here maybe at node 1 we define maybe a pin support, and at node 2 we define a free support in X but still pinned, and apply a standard load, maybe for this slender cross section 1 kilonewton in downwards direction plus a small compression in X, maybe -5. And now we can run a design, and if we run design we will see that everything is good, I hope. So program is designing ULS and SLS, so I will reduce this. So you see design is 65%. If I watch the, let's say, forces of static analysis, I see I have a deflection of almost 9 millimeter. If we check normal axis force, we have this increased according safety pressure. We have no shear forces. We have only shear force in perpendicular direction, no torsional moment, only a bending moment, no biaxial bending. Yeah, and the stress, maybe only to get a feeling, is about 135 MPa or Newton per square meter. So everything fine, but still we have to see, if we watch basic stress, we have on the top pressure, and this pressure have some effect. And now you should, if you start designing some stuff like this, of course you should ask some questions. And the first question is, can my program, or how can I check local buckling according to this pressure? And let's say check what the design is doing, and if we go to the pressure, we will see here is the check for it in the middle, and the easiest thing is, let's say as Dlubal engineer, I see directly, oh, he used effective sections, but you have here an application to see. For normal axis force, he grabbed out here from the web something and increased stress on the lateral sides to cover this effect of local buckling. The same for the bending MY, he have no problem, and for bending MC, he also grabbed out something here. So yes, local buckling is considered. Now we come to the question global buckling. Let's say we checked it according theory second order on deformed shape, but the easy one. But we found out we have no bending moment and no biaxial bending. What is, let's say, a point that I have no effect out of plane. And this brings me to the situation that I say, yes, I should consider an imperfection to activate this effect. How I can do this in the program? Is it possible? And I say, yes, it's possible. You have here imperfection. Of course, we should consider it in one and in the other direction, so I simplify it only in one direction. I say, okay, please make here one imperfection, maybe a both imperfection, because it's supported on both sides according to Eurocode. In Y direction, elastic, and place it here, and you see we have one imperfection here. No? Then we check the situation about combinations. So we say we only want to check ULS, so I remove this, and we say it should be checked according large deformation analysis, and the imperfection should be considered. And if I do this, I, let's say, come closer to the situation, what happens in this member according to this load. I hope at least. And now I see, oh, deflection increases, and we see a warning message, and we see maybe if we check deflection, we have here almost 60 millimeters. The normal axis force is not constant, what is pretty strange. We have now shear forces in both directions, we have small torsional moment, we have a bending moment, and the stress is about 471, so really strange, and higher than the utilization, so higher than the allowed stress. So now the point is coming, we used large deformation analysis, we used imperfection. Is it real, or should we do something more? And the point is, yes, you have to do something more because you have a torsional moment. This brings me to the situation we should clarify at which place the load is acting. So at the moment the load is acting in the center of shear, what means it's behind. But I place it now in reality here on this beam. No? If I do this, it will be more worse because it really induces now torsion, and you see the deflection is going upwards, and also the stress is now much bigger, so it's going not better. So in begin it looks pretty easy, but now you see, oh, you suffer a lot of issues. And the point is, we have an open cross section, thin wall cross section according 6 degrees of freedom, and this 6 degrees of freedom cannot handle this torsion pretty good. So what should we do? For this we should activate the torsional warping analysis, 7 degrees of freedom, and if I do this, I get a real condition. I can follow the mechanics in real according everything what is defined. So we have an imperfect system, we have an eccentric load, and we have 7 degrees of freedom. And now you see you have also more forces. You get here the normal axis force, now it's constant. You get the shear forces, you get a torsional moment, bending moment, biaxial, minor bending, warping, primary torsion, secondary torsion, and also a warping deflection. And now we are interested, of course, in the stress, and you see, okay, stress is at 980, so pretty high. Yeah, of course, because we have this warping here. And now what should we do? I would say this model is not working so far. You have to support it, or you have to give him a stability support, because if you watch the deflection, you will see your member is buckling, or let's say lateral torsional buckling out of plane, and this is too much. So we should let's say add here a node in the middle, for example, at 50%, and apply here a support in the y direction, y and a rotation support. This could be a support or also a beam from your photovoltaic system. And if you run now analysis, we should see that the stability support, what is not working against the main bending, yeah, brings us back to the good deflection, and also to a stress state what is okay. And if we run now still design, you will see we also, with consideration of local buckling, we have a utilization what fits. And this is the point what is really interesting. These photovoltaic systems are no easy systems, because you have really cross sections what are challenging you, and it's not visible, because you have to know that this part of these special elements have really some effects what should be checked. And the next topic is maybe not only the cold formed stuff, then also if you have some extruded aluminum, it's working almost similar, but you have to get from the manufacturer the DXF. You can import it here, then you get here this line model. This is not calculatable, but we have here some automatism what can model the cross section quite easily, can define the stripe elements. Only here have some issues, so you can define here maybe a coupling, and let's couple these elements here, yeah, and fulfill it with material. So say here, okay, we have in reality here a material for bending check or bending stiffness, maybe also here. And now if we run it, we get results. We get here cross section values as needed, and you can save this stuff in maybe download folder, rail, and you can use it here in RFEM, similar like all other section. Go to the library to R section and connect it, maybe download folder, rail, and get it in RFEM. So it also solves your questions about how can I get this cross section in the program for design. Easily model it with our cross section program RFEM, and you have it here in program. So now let's come to the next topic, the investigation of the module load bearing capacity. What means this? I speak about the glass panes which holds the layer of photovoltaic systems. What means or what handles the question, do you know if you have some special load situations, maybe like a snow load accumulation or man loads, if the glass panels can handle the loads? So I picked out this photo. Of course, it looks like that the modules fall down to the bottom, but what I really liked in this photo is the shape of the panels, that they have really a sag in it, and this should show you that the glass panels can deform and will deform, and if you have a situation that you should check it, you can do it. And here our program gives you also an answer how you can check special load situations on these modules. And also, for example, think back to the first picture with the snow load on the roof, or the farming house where we have a gripping in the roof. To check these special load conditions on the glass panels, you can use our glass design program and find out a utilization by defining the glass like it is. And for this I prepared also an example. Here you see open here investigation. Yeah, exactly. So here I modeled, or let's say to show you how it's working. You have in RFEM the option here, if you want to design glass, you can activate it here. Of course, you can define here the load cases. I defined here special load situations such as snow load accumulation, and I defined the glass panel here with a special glass composition, where I defined a thickness of 3.2 millimeters with a heat strengthened float glass, and I connected it hinged to the, let's say, boundary members, and the boundary members are aluminum rail around what are connected to the supports. And if you design it according this load, you will receive a utilization, and you see, oh, okay, this load could be taken from the glass pane plus rails, and you have a utilization around let's say 98%. So it, for the RFEM program, it's completely uninteresting if you have a photovoltaic system, if you have a glass pane, if you have a steel, how you can model everything in this environment, and it's really a problem solver. But before, if you make a research and see, oh, I have to check maybe the effects from the underlying system, and it produces some loads on my glass panes, how can I check it? Because the solar panels have only a spreadsheet would say, oh, it allows 1.1 kilonewton per square meter, then you can't say something, but here you can calculate it like it is. And now let's come to next typical situations. What will happen if you are working in this field? You have to process a lot of similar models, because photovoltaic systems, let's say, if you start talking about, you think, oh, you have only systems on roofs and it looks almost similar. Yes. Or on fields it looks similar. Yes, I agree. And what I see as, let's say, as software developer, I see you have to handle it all the day, always a small, almost similar models, and you have to hold organization up to know which model belongs to which project. And also secondary, what I also see, if you have always to solve similar models, you should think about how can I make it more efficient, not to define hundreds of models what looking similar day by day. It's a time eater, I would say. To give you a picture, see these 3 houses. Let's say we have 3 photovoltaic systems on it. Maybe one house, one project have 2, the middle house have 3, the right house have only 1. Every client paying extra, every project is separately. For you it's almost similar, maybe the sizes are different a little bit, but you have to organize it. And for this we, let's say, offer a program, we offer a manager tool, a project manager, where you can organize your project, visual, move it to other folders as needed. It's a better Windows project Explorer with more information for engineers. And this I want to show you. You see here in RFEM 6 here these blue buttons. You have here this Dlubal Center, and what is, let's say, quite interesting, you see all projects what are included in this folder of Windows. You directly can pick on it, you can zoom in, you get information about models, you can visualize it with a picture, you can visualize it like a table, you can bind in new projects by connecting a folder. So if you need, for example, here project A, B, you can place all your projects in it and visualize it like this or visualize it like this. So both is possible, and this tool should help you to be updated, yeah, and to have a good order in this case. And further, you see now what is maybe my story, what I want to tell you as next. This Dlubal Center have not only models, then it have model templates where you can maybe store templates for working with timber or steel or whatever, and also blocks and joint templates. So the joint template should inspire you if you have to do a lot of with photovoltaic systems what are almost similar. You see, you can handle it a template directly with such a database. Oops. And therefore it's interesting to make the daily job a little bit more efficient, to organize it in this way. Now, if you have almost similar systems, and for this I open a new model, an empty model, for example a photovoltaic system, because this is the story behind. Maybe use TT. You can use our, let's say, block manager, where we define some blocks. And the question is, which blocks? What is a block? A block is for us a special fraction of model. Like if you know Lego bricks, it's one brick and you can assemble it. You see, for example, you have here trusses. You have here 2D trusses, you have here 3D trusses, you have all trusses. But today we speak about photovoltaic, so we go to renewable energy. We have photovoltaic cells, we can make it a little bit better. And you see this is coming from Dlubal side, what means we have here blocks with this white background from our side, with the dark blue background are user-defined categories. And if I double click it, this means you get an environment, let's say an intermediate environment, where you see this photovoltaic block. Of course it's overwhelmed by numbering and by maybe dimensions. Now it's a little bit more clear. You can rotate and zoom, but you cannot model here. But you have here a tab where you can, let's say, rule how this model is looking like. You can say, I want to have maybe 4 spans. Then you get one more. You can say, my span should, the third one should have only 5 meters. You change it. So it's possible. Yeah, and if it's satisfying, you say okay, then the program is moving this type of model in your main space for further working like I showed it today. If you say I made an error, you draw the mouse and you see the program is drawing such a box around. Yeah, you can double click the box and come back to this intermediate environment to change something again. Okay, so this is the first story. What I want to say is, here in the block manager are models what could be or what working not according defining nodes and members and according defining these parameters here. And now the question is, where these parameters are coming from. Of course, these are made from our programmers, but it's only an example. You see here, this is a block according type JavaScript, and you have here also a JavaScript sheet. And if you take a closer look, you see you have here a function input data, what, let's say, describe exactly the number of spans, height, distances, what is mentioned here. So this stuff here is giving this input. And in the second part, you have here function generate, what using this, let's say, distances, angles, and all this stuff from the upper input, and models nodes, hinges, members, and so on, that you get this full model what we show or what we see in this structure here. And now let's say I'm coming to the point. This stuff is only an example, but you can open the log and you can program it by yourself. So it's for you. It's a tool where you can parameterize your, let's say, almost similar models to be much quicker, because then you only change the inputs and insert it. And this should simplify your work a lot. And when we started now here by saying, oh, this is a typical challenge of an engineer in field of photovoltaic systems. Yes, you have to process a lot of similar models, but our program gives you a lot of tools to organize it. To hold overview with block manager and to create new blocks to be more efficient in modeling. And now let's say we come to our last point of this session. In many countries, a verifiable static calculation must be submitted. Let's say I call it simply document. You have to write down what you did, what you considered, and you have to create a document. Of course, you can do it by Word, and this is suffering, I would say, because if you change something, you have to update it and update it according every change. This makes work life not really easy, and I want to make it much more complex. You have to write down what you did and what you designed, and this is only one check here. You see, this is a cross-section check for axial and shear stress. It's done by a square root and it gives out a utilization. So this is one check what is done for every node or for every load case situation hundreds of times, and you have to find out the most worst result. This is done generally by let's say by a calculation program, but now you have to document also this stuff, and not only for these formulas and for hundreds of formulas. Imagine or remember back to the buckling of cross-section and so on. And maybe to give a solution, our program have also an environment to create a document for all inputs and on analysis what you did. To show you how it's working, let's open a model to present. And here you see a model, so it's only 2D model, design is made, design is, let's say, at almost 60%, and now you want to document because you considered a lot of things here in this stuff, and you see in the end you have printout report. You can create a new printout report. You can say save and show, and the program is creating a report here. You see with several pages, it has 35 pages, you have a cover where you can define your client, who created it, which project, the overview picture, small content, and the next page you get a big content. You get a description of all cross-section, of all materials, of all members, and so on, of all loads with directions, of results of designs for every member, which checks, which utilizations, a design check overview. So you get really a document, and if you say, okay, I want to make it more readable for my user, it's possible. So if you say you need this sketch here, maybe with numbering, then go to the printer, print it to report, and maybe say here window filling and save and show. Then you get this picture here in the report. No problem. If you say you need also maybe loads, then go to the printer, say I have a multi-print, no model views, only load cases, the load cases 1 to 9, only from the current view with imperfections, add-ons are not needed, and save and show. Then you get here in the report also pictures of loads. Yeah, so this is really an adaptive interactive document. You can have it parallel, and you can document everything what you did and output it later to RTF, PDF, HTML file. And if you need it in another language, what is also possible in this branch, because if your company export it to any other country, you have here an option to say set language from English to, oh, I had it in English, so maybe now in German, so let's translate it or to German, then you get it in German. Yeah, or you need it in any other language, so it's open, and this solves your task what you have in this branch, and should bring you forward and save your time. And now I'm in the end of this session. Maybe to catch up everything, we spoke about impacts, we spoke about underlying systems, finding optimal systems, cold forms, or let's say cross sections, module capacity, processing similar models, and documentation. So what is for me important to say, you can find impacts or basic impacts in our GeoZone tool on website or connected to our program. If you have to consider or in the calculation special stiffnesses from underlying system, no problem, RFEM is ready to it, you can model it like it is. If you have to find an optimal system, you can bring in eccentricities, different materials, you can mix it up with this is what is needed, and you can design it with our design add-ons. Steel, timber, concrete, aluminum, glass, whatever, which material you have, you can mix it also in our system. If we speak about cross sections, our design add-ons are ready, but if you have some user-defined sections, you can use our section program to it. And finally, about processing similar models, I showed you, of course, our Dlubal Center, what is main part of the program, but also the blocks with JavaScript technology. This is one option, but if you say you are a global player, you have also maybe you're working over the world and you have some other programs what all should work with calculation in background. Be sure our program offers also API to connect it, so you can use it also in background. Only ask us for some support. And finally, if you have to document it, all our calculations could be closed with a full document with tables and pictures. And this brings me now really to the end, and I thank you for listening and watching, and give back.
Thank you, Andreas, for your nice presentation. I have an additional hint. You can book our online courses, the RFEM 6 Masterclass course. It's a course for beginners. Then the Eurocode 2 course for the reinforced concrete design with RFEM 6. Then the Eurocode 3 course for the steel design. The Eurocode 5 course for the timber design. And there are also course packages available. For more information, just scan the QR codes in the middle or click at the links at the bottom. Okay, that's also all from my side. I thank you for your attention. Thanks to Andreas Niemeyer for the presentation. I wish all a nice rest of the day. Bye-bye.